Okay, ready to dive in.
Absolutely, let's do it.
Today, we're looking at this fascinating paper about, well, rigging games, basically.
Oh, yeah.
But it's not just about cheating, right? It
Yeah.
gets into some deep mathematical territory.
Absolutely. It all boils down to manipulating probabilities using math to shift the odds in your favor.
That's right.
It's called beat the average, and it's deceptively simple.
So beat the average, huh?
Yeah.
What's the game all about?
Imagine 3 identical dice are rolled.
Okay.
You pick one,
But
and if yours is higher than the average of the other 2, you win.
sounds pretty straightforward.
Right. On the surface, it seems totally fair, especially with standard dice.
Yeah, you'd think so.
But the paper asks a really sneaky question. Can you design special dice that give the casino an edge?
So that's where the rigging comes in.
Exactly. It's a puzzle they call the casino owner problem.
I love that name.
It's a good one.
So how do they even begin to figure that out? Where do you even start with designing rigged dice?
Well, they start simple with like a one-sided die.
That's not much of a die.
Right. The player always wins, so not very interesting.
Yeah, not much of a game there.
Then they move on to 2 sides, like a coin flip.
Okay, getting a little more complex.
In that scenario, the casino can actually get their winning probability up to about 0.385.
That's a pretty big jump from 0.
Yeah, but they'd still be losing money on average.
So still not a profitable scam for the casino.
Nope. So they bump it up again to a 3-sided die
Okay, 3 sides.
with the values 1, 2, and 4, each equally likely.
Interesting choice of numbers.
It is, and with that setup, the casino almost breaks even.
So they're getting closer and closer to having the upper hand.
Exactly, they're starting to crack the code.
What about the card version of the game? How does that work?
Same rules, but instead of dice, you've got a deck of cards.
Okay, so each card has a unique value.
Right, let's say you have cards numbered 1, 2, and 4.
Just like that 3-sided die example.
Yep, but here's the kicker. The player's winning chances drop to just 13.
Wait a minute, why such a big difference? Just by switching from dice to cards.
It all comes down to how the specific values interact with the average.
Interesting.
And now hold on tight, because this is where it gets really cool.
All right.
Proposition 1.4 in the paper states that no matter how many cards you have in the deck, the casino's winning probability can never go above 23.
Seriously? So even if you had like a million cards, they're stuck at that 23 limit.
Exactly. It's a hard limit.
That's wild. How do they even prove something like that?
Well, they actually offer 2 different proofs, which shows how important this 23 limit is.
2 proofs. That's serious math.
It is. The first one uses something called the probabilistic method.
Okay, I'm vaguely familiar with that.
It basically shows that if you shrink the deck size, the casino's chances of winning don't get any worse.
Interesting.
So imagine you have a 100-card deck, and you randomly pick 3 cards.
Okay, got it.
The odds of the casino winning in that scenario are exactly the same as if you just played the game with those 3 cards alone.
So it's like the smaller deck captures the essence of the larger one.
Yeah, exactly. And since the maximum winning probability with a 3-card deck is 23, that limit applies to any deck size.
Wow, that's clever.
Right. It's a really elegant way to prove this.
What about the other proof? How does that one work?
The second proof is a bit more technical, but it essentially boils down to the fact that only 2 out of 3 players can win at the same time.
Okay, I think I get that.
Like if you think of the 3 cards being drawn as 3 players, only 2 of them can have a card higher than the average of the other 2.
Makes sense. So they've nailed down the card version.
They have.
But how does this all connect back to those rigged dice we were talking about?
Well, think of dice as just a deck of cards with many, many copies of the same card.
I never thought of it that way.
Theorem 1.5 in the paper is the bridge between the 2.
Okay, tell me more about that.
It states that the casino can design dice to get their winning probability as close to 23 as they want.
Wait, really? But how many sides do they need on these crazy dice?
Surprisingly, they can start getting an edge with as few as 18 sides.
18 sides. That's a lot of sides for a die.
It is, but remember, they're trying to mimic that card deck with values like 1, 2, 4, and so on, with equal probability for each side.
Okay, yeah, that makes sense.
But there's a catch.
Uh-oh, what's the catch?
They can get arbitrarily close to 23, but they can never actually hit it with real dice.
So those perfectly unfair dice only exist in the world of math equations.
Exactly. In the real world, you're limited by the physical constraints of how many sides a die can have.
Okay, so no casinos are going to be rolling around 100-sided dice anytime soon.
Probably not.
But even getting close to 23 gives them a significant advantage.
Absolutely. Even a small edge can translate to big profits over time.
This is all blowing my mind.
It's pretty wild, right? And it gets even more interesting when you consider the bring your own die variation they introduce.
Bring your own die. What's that all about?
Imagine you get to choose the die, but the casino still wins in the long run.
How is that even possible?
Because that magical 23 probability is unattainable with real physical dice.
Ah, so no matter how clever I am in designing my die, the casino always has a slight edge.
Exactly. It highlights how this game is just one example of a much broader mathematical concept. Optimizing the expected value of a function over independent and identically distributed random variables.
Whoa, hold on. That's a mouthful. Can you break that down for me?
Sure.
They're basically saying this problem, this casino owner problem, is just the tip of the iceberg.
Okay.
It's part of a whole class of problems where you have multiple random variables, things that are unpredictable.
Like the roll of a die.
Exactly. And the goal is to find the best way to arrange those random variables to get the best possible outcome on average.
Okay, I think I'm starting to get it.
They formalize all of this with problem 2.1 in the paper, which sets the stage for the rest of their analysis.
So we're going from a specific game of chance to a more general mathematical framework.
Exactly. And it gets pretty deep from here.
I can't wait to dive in.
Me too.
But first, we need a break. Let's take a quick one and come back to this amazing world of probabilities. And we're back.
Ready to tackle the rest of this paper?
Absolutely, let's do it.
So, before the break, we were talking about how the casino can get arbitrarily close to that 23 winning probability with rigged dice, but they can never actually reach it.
All right.
Why is that? What's stopping them from achieving perfect unfairness?
It comes down to those pesky real-world constraints.
Always getting in the way of our perfect mathematical models.
Exactly. In this case, it's the fact that dice have a finite number of sides.
Ah, so you can't create a perfectly smooth probability distribution with chunky physical dice.
That's the idea.
Like trying to paint a perfect circle with a square brush.
Aha, exactly. You can get close, but there will always be those jagged edges.
So those perfectly unfair dice, they only exist in the realm of pure math.
That's right.
But, as we saw with that four-sided dice example, even getting close can be pretty darn effective.
Oh, absolutely. A slight edge is all it takes for the casino to rake in profits over time.
It's a good reminder that appearances can be deceiving, even in something as seemingly simple as a dice game.
Always a good idea to look beneath the surface.
Speaking of deceiving appearances, what about that bring your own die variation?
Ah, yes. That one really highlights the subtle power of this 23 limit.
Remind me how that one works again.
You get to choose the die.
Okay, so I have complete control over the design.
You do. You can be as clever as you want, use any values you can think of.
Sounds like a surefire way to beat the casino.
But there's a catch, remember? That magical 23 winning probability is unattainable with real dice.
Right, because of that finite sides thing.
Exactly. So no matter how you design your die, you'll never be able to create a distribution that gives the casino a 23 winning probability.
So there will always be a tiny sliver of advantage for the casino, no matter what I do.
That's the beauty of it. Even when you think you have complete control, the underlying math is working against you.
It's a rigged system, man.
Well, rigged might be a strong word.
Okay, maybe not intentionally rigged.
It's more like a subtle bias baked into the very structure of the game.
A bias that can be exploited by those who understand the math.
Exactly. And that's what makes this paper so fascinating.
It's not just about exposing a cheat, it's about understanding a fundamental principle of probability.
And this principle goes way beyond casino games.
Right, we were starting to get into that before the break.
Let's dig deeper into that general mathematical framework they introduce.
Okay, I'm ready for some serious math.
They generalize this whole idea of rigging dice and cards to something called optimizing the expected value of a function over ED random variables.
Oh, hold on, slow down. I need to process all those words.
Fair enough.
Let's break it down one piece at a time.
Okay, first we've got ED random variables.
AIDS, what's that stand for again?
Independent and identically distributed.
Right, so each variable is like its own separate coin flip, not influenced by the others.
Exactly, like those dice rolls and beat the average.
Got it.
Then we have a function, which is basically a rule that takes those random variables as input and spits out a number.
Okay, so it's like a recipe that uses those random ingredients.
Exactly. And the expected value is just the average outcome of that function over many, many trials.
So like if we played beat the average 1,000,000 times, the expected value would tell us, on average, how much the casino would win or lose.
Precisely. Now, the big idea here is to find the best way to arrange those 18 random variables to choose their values or probabilities so that you maximize the expected value of that function.
So it's like a supercharged optimization problem.
Exactly. You're not just looking for any solution. You're looking for the best possible solution.
And this applies to all sorts of real-world scenarios, right?
Absolutely. Think about managing investments with unpredictable returns, optimizing logistics with fluctuating delivery times and customer demand, or even designing algorithms that have to deal with noisy data.
So it's like a universal toolkit for dealing with uncertainty and making the most of it.
That's a great way to put it. And the techniques they develop in this paper, like those perturbation methods we were talking about, are essential for solving these types of problems.
It's amazing how something as seemingly frivolous as rigging a game can lead to such powerful and widely applicable mathematical insights.
That's the beauty of math, isn't it? You never know where exploration will lead you.
This is all pretty mind-blowing stuff. I'm ready to hear more about how they apply these techniques to specific problems.
Okay, let's dive into a really challenging example they tackle.
Lead the way.
All right, so remember how we were talking about that magical 25 probability?
Yeah, that theoretical limit for this inequality problem.
Right. So now they start digging into what that optimal distribution, the one that would actually achieve that 25, what that would even look like.
Okay, so they're painting a picture of this perfect solution, even though it might not be achievable in the real world.
Exactly. And one of the first things they point out is that this optimal distribution can't have what they call an atom at 0.
An atom. Now, I'm no physicist, so can you break that down for me? What does that even mean in this context?
Sure, think of it this way.
Okay.
Imagine a probability distribution as like a landscape, right?
Okay, I can picture that.
An atom is like a really sharp peak in that landscape.
Oh, I see.
A point where all the probability is piled up instead of being spread out smoothly.
Got it.
So they're saying that if there was an atom at 0, meaning there's a chance, even a small one, that one of the variables is exactly 0,
Okay.
then you could always tweak the distribution a little bit to get a higher probability.
Interesting.
Like smooth out that peak and spread the probability around.
So this ideal distribution, it can't have any sharp edges. It needs to be more like a rolling hill than a pointy mountain.
Exactly. It needs to be smooth to really maximize that probability.
Makes sense.
And it gets even more interesting.
Oh.
They also say that this optimal distribution can't be finitely supported.
Now you've lost me.
Basically, it means it can't be limited to just a few specific values. Like a 6-sided die has finite support, right?
Yeah, just 6 possibilities.
But this optimal distribution, it needs to have probability spread out over a whole range of values, not just concentrated on a few.
So no dice, no cards, no simple solutions.
Nope, this thing is a wild beast. It lives in the world of continuous math, not the discrete world of our everyday objects.
So we can imagine it, we can describe it with equations, but we can't actually create it in the real world.
That's the idea.
It's like this perfect mathematical object that we can glimpse, but never fully grasp.
It's a reminder of how powerful math is, but also of its limitations.
Okay, so we've got this unattainable ideal distribution.
Yep.
But they don't just stop there, do they? They also explore the concept of fair games.
Right. They shift gears a bit.
Instead of trying to rig the game, they ask, how do we make it truly fair?
Exactly. They're looking for the sweet spot where both sides, the player and the casino, have a 50-50 chance of winning.
Okay, but how do you even find that perfect balance point?
Well, they frame it as a challenge, basically.
A challenge for mathematicians to solve.
Exactly. It's not a simple problem.
I bet it's not.
You need to figure out the exact relationship between those random variables, the specific inequality, and the probability distribution that would make everything perfectly balanced.
So it's like a multi-dimensional puzzle.
It is, and they don't give us the solution in this paper.
They're leaving it as an open problem.
They are. It's an invitation for further research, basically.
To explore this idea of fairness in a deeper, more mathematical way.
Exactly. It's a really cool direction to take this research.
Wow, this whole deep dive has been incredible. And we've gone from rigging dice to exploring the very foundations of probability and fairness.
It's amazing how much depth there is to this seemingly simple game.
It really highlights the power of math to illuminate the hidden structures of our world, even in something as basic as a game of chance.
And who knows what other amazing discoveries are out there just waiting to be uncovered.
That's the beauty of it, right? The exploration never ends.
Absolutely. There's always more to learn, more questions to ask, and more mysteries to unravel.
On that note, I think we'll wrap up this deep dive.
It's been a pleasure exploring these ideas with you.
Likewise. And to all our listeners out there, keep questioning, keep exploring, and keep diving deep into the fascinating world of math. Okay, so you sent me this research paper about probabilities, right? And getting the average,
Yeah,
optimizing over IID distributions, and they beat the average game.
that's the one.
It sounds a little intimidating, honestly.
It sounds very technical, yeah, but it actually uses a very relatable example, like a casino game. Imagine you're trying to beat the average roll of some dice.
Okay, now I'm intrigued. Like, how does this game work? Tell me.
So it's quite simple, really. It's 3 identical dice.
Okay.
All 3 are rolled, and you get to choose one of them.
Okay.
And you win if the value on your die, the one you choose, is greater than or equal to the average of the other 2.
At first glance, it sounds like the odds might be in the player's favor.
Right.
Because, like, there's a decent chance of at least one of the other 2 dice being lower than yours, right?
Yeah, that's what makes it so interesting.
Yeah.
Intuitively, it feels like you have a good chance of winning. But this is where it gets fascinating. The casino, they can actually design the dice in a way that gives them a surprisingly high probability of winning.
So we're not talking about, like, standard fair dice here.
No, not at all.
How does the casino manipulate the dice?
The key is probability distributions.
Okay.
You see, like standard 6-sided dice, they have a uniform distribution, meaning each face has an equal chance of appearing.
Okay.
But the casino can use dice with non-standard distributions,
Right.
where some faces are more likely to come up than others.
So like those loaded dice you see in movies.
Exactly.
But instead of just like weighting one side, they're manipulating the entire distribution.
Exactly. And the paper systematically explores this by analyzing what happens as the number of sides on the dice increases.
Okay.
So they start with the simplest case, a one-sided die.
One-sided die, that's just a sphere.
Well, think of it as a die where every face shows the same number.
Okay.
And in this case, obviously the player always wins. No matter what number is rolled, it will always be equal to the average, right?
Yeah.
So that's like the worst case scenario for the casino.
Makes sense. They need variation to have any chance of winning.
Yeah.
What happens when they move up to a two-sided die?
Well, with 2 sides, think of like a coin flip.
Yeah.
0 and 1. The casino can start to tilt the odds a little bit.
Yeah.
The paper calculates, and the best they can do with 2 sides is achieve a winning probability of 0.385, roughly.
So even with just two sides, they're still losing more than they're winning?
Yeah, a lot more, yeah.
But it's a step up from the one-sided die.
Right, where they had no chance at all.
Right, exactly. Okay, so let's jump to a 3-sided die.
Okay.
What happens then?
So the paper uses an example, faces showing 1, 2, and 4.
Okay.
Each with equal probability. Even with this, the casino's winning probability jumps up to 0.481, approximately.
Wow, okay.
Yeah.
So they're almost at even odds with just 3 sides. I'm starting to see how the casino can really shift things by just like tweaking those probabilities.
Yeah.
So what happens is they just keep adding sides.
Well, as the number of sides increases, the potential advantage keeps growing.
Okay.
They have more flexibility to create these kind of skewed probability distributions where certain values are much more likely to appear than others.
Right.
And the paper shows that with enough sides, the casino can get their winning probability very close to 2/3.
Wait, 2/3. Okay, now hold on. That's a huge advantage.
It is, yeah.
But how do they actually figure out what those optimal probability distributions are?
That's where the paper gets really clever.
Okay.
They shift gears and analyze a card version of Beat the Average,
Okay.
which turns out to be easier to analyze mathematically.
Okay.
Imagine a deck of cards with, distinct values.
Okay.
3 cards are drawn randomly, and you win if your card's value is at least the average of the other 2.
So it's the same basic concept.
Same concept.
But with cards instead, what's the advantage of that?
So the key difference is that with cards, we're drawing without replacement.
Oh.
Once a card is drawn, it's out of the game.
Right.
This eliminates the possibility of getting the same value multiple times, which you can have with the dice.
Okay.
And here's the amazing part. The paper proves that the casino's maximum winning probability in this card version is always 2/3.
2/3, just like with the dice.
Exactly.
Okay, but how do they prove that?
So they use a technique called the probabilistic method.
Okay.
The key idea is that they analyze what happens when you randomly remove cards from the deck to create smaller decks.
Yeah.
And they show that the winning probability for at least one of these smaller decks must be at least as high as the original deck.
Okay.
And since we know the maximum winning probability for a 3-card deck is 2/3,
Right.
they can deduce that it can't be higher for any larger deck.
So they're basically working backwards.
Yeah,
Using the smaller decks to set a limit.
that's right.
That's clever.
Yeah.
Okay, but how does this connect back to the dice?
So think of rolling many-sided dice
Right.
as being similar to drawing cards with replacement,
Right. Okay.
where each card is put back into the deck after being drawn.
Right. Okay. Yeah.
So the paper uses this connection to kind of bridge the gap between the card and the dice version.
Ah, I see. So they're using the insights from the card game where they have this solid proof
Yeah,
to shed light on the dice game.
that's right. And they find that the casino can design dice to get arbitrarily close to that 2/3 winning probability.
Okay.
And they achieve this by using a very specific pattern on the faces of the dice. Powers of 2.
Powers of 2. Is there something special about that sequence?
So it turns out this particular arrangement creates a distribution that, as the number of sides increases,
Mm-hmm.
gets closer and closer to that optimal distribution they found in the card game.
Okay.
But here's a fascinating thing, right? They can only get arbitrarily close. They can never achieve it perfectly with discrete dice.
So there's this fundamental limit
Yeah.
built into the nature of dice.
It has to do with the discrete nature of dice.
Okay.
No matter how many sides you add, right?
Mm-hmm.
You'll always have a finite number of faces.
Okay.
This discreteness, right,
Yeah.
prevents the probability distribution from perfectly matching the continuous distribution that would be needed to get exactly 2/3.
So it's like trying to draw a perfect circle using only straight lines.
That's a great analogy.
You can add as many sides to your polygon, but it'll never be a true circle.
Exactly.
Yeah. Okay, so this has some really interesting implications.
Yeah.
Let's imagine a scenario where the casino says, hey, you can bring your own die to the game.
Okay.
So they'll still roll 2 of their special dice, and you roll yours, and they win if the average of their 2 rolls beats your roll.
Okay. Interesting.
Now, it sounds like the player has an advantage. I would be tempted to bring the most unfair die I could possibly find.
Right.
Weighted as much as I could.
But remember, no discrete die can hit that exact 2/3 winning probability.
That's right. It comes back.
It always comes back.
So even with that freedom to choose, you're still limited.
Absolutely. Yep.
The casino still has the edge.
Still got the edge.
Wow. Okay, so they've set up a system where they always have an advantage.
Always have a little mathematical ace up their sleeve.
So this beat the average game, it's more than just this like fun challenge.
Right.
It's telling us something about probability
Yeah.
and the limits of what we can do with discrete objects.
Absolutely. That's exactly right. And what's even more remarkable is this casino game is just a specific example
Okay.
of a much broader mathematical question that the paper explores. How to maximize the expected outcome when you have a certain function and independent variables.
Okay, so that sounds a bit abstract. Can you give me a more concrete example?
Imagine you're trying to optimize a manufacturing process.
Okay.
And you have various inputs,
Yeah.
you know, raw material, temperature, speed of machines.
Okay.
And you have a specific output that you're trying to maximize,
Uh-huh.
maybe the strength of the product.
So you're trying to find the sweet spot for all those variables
Exactly.
to get the best output.
And the paper provides a general method for these kinds of optimization problems,
Okay.
which involves analyzing the average outcome over all possible combinations of input values.
But how do you analyze all of those combinations? Especially when you're dealing with probability.
Right. Well, that's where they delve into more mathematical tools. One key technique is maximizing the probability of an inequality being true. So, for example, like x1 plus x2 plus x3 is less than 2x4.
Okay, I can see how that's similar to the dice game.
Right.
It's comparing the value of one to the average of the others.
Exactly. And one crucial point is that you need to use a strict inequality, like less than.
Why is that important?
Well, if you use less than or equal to, you can get trivial solutions where all the values are 0.
Oh, okay.
The inequality is automatically true. So by using less than, you're forcing the system to find more meaningful solutions.
So you're making the puzzle more challenging.
Exactly. And to illustrate the method, they apply it to this specific inequality,
Right.
showing the highest possible probability of it being true is somewhere between zero point 0.4 and 0.422.
So they've narrowed it down,
Yeah,
but they haven't found the exact maximum.
not yet. That's right.
So that's where they leave us with a question to solve.
Yeah, pretty much.
But didn't you say they use some clever tricks? I want to hear about those.
Absolutely. So one technique involves introducing small random perturbations to the variables in the inequality.
So they're shaking things up,
That's right.
seeing if they can find a better solution.
Precisely. These random perturbations can help them find better bounds. They also use computational methods,
Okay.
like mixed integer linear programming,
Uh-huh.
or MLP,
Right.
to search for optimal solutions.
So they're using a combination of tricks and computational power. Okay. Very clever. I'm impressed.
Yeah, they're definitely pushing the boundaries.
Yeah. And what's fascinating is, while they were using MLP to find better upper bounds, they stumbled upon this pattern.
A pattern, yeah.
Tell me about this pattern. I love a good pattern.
Remember how the casino used that distribution with powers of 2 on the dice
Yeah.
to get close to that 2/3 winning probability?
Uh-huh.
Well, the solutions produced by their MLP algorithm seem to mimic that same pattern,
Wow. That's wild.
isn't it?
It's like the algorithm rediscovered this powerful approach.
Independently, yeah.
Does this mean they've cracked the code?
It's a very promising lead, but not quite a definitive solution.
Okay.
Based on their observations, they formulated a conjecture,
Okay.
the 2/5 conjecture.
2/5 conjecture. Okay, what's that?
They believe that the lower bound they found for the maximum probability of that inequality is actually the exact value.
Okay.
In other words, they're betting that 2/5 is the absolute best you can do.
Okay, so they're putting their money on 2/5. But do they have a proof?
Not yet.
Not yet.
While the patterns suggest 2/5 is correct, a formal mathematical proof still needs to be done.
This is what I love about math.
What's that?
There's always another layer to uncover.
Always a mystery.
And it sounds like we've only begun to explore this paper.
We just scratched the surface.
I'm ready to keep digging.
Let's do it. So let's pick up where we left off with that attainability thing.
Okay.
Remember, the supremum, it's like the holy grail in these optimization problems, represents the best you could theoretically achieve.
Right. But just because it's theoretically possible doesn't mean we can actually get there.
That's right, yeah.
Are there situations where we can't reach the supremum?
That's a great question. And the paper actually hints that, yeah, the supremum might not be achievable for certain types of distributions.
Okay, what kind of distributions are we talking about?
Think back to our casino game. With those dice with powers of 2, as the number of sides gets large, the distribution starts to look more and more continuous. But with real dice, you always have a finite number of sides.
Right.
That discreteness seems to be a fundamental barrier.
So it's like trying to perfectly replicate a smooth curve
Yeah.
using only straight lines.
Yeah.
You can use as many as you want, but
Well,
you'll never get a truly smooth curve.
Exactly. And the paper goes a step further. They prove that if your probability distribution has an atom at 0,
Okay.
meaning there's a non-zero probability of getting a 0,
Okay.
then it cannot be an optimizer.
So having that probability at 0, it's like a red flag
Pretty much, yeah.
that you haven't found the best strategy.
Precisely. And this leads to an interesting observation. Since any distribution with a finite number of atoms will always have one at 0,
Okay.
it means no finitely supported distribution can be an optimizer.
Hold on, break that down. What's a finitely supported distribution?
Sure. So a finitely supported distribution just means that all the probability is concentrated on a finite number of values,
Okay.
like a die with a fixed number of sides.
Right.
Each side represents a value. There's no probability for values that don't appear on the die.
Okay, I see. So to even have a chance of reaching the supremum, you need a distribution that's spread out over an infinite number of values.
Exactly, yeah. We need a distribution that's more like that smooth curve.
Okay, this is getting pretty heady. So even with these more sophisticated distributions, are we guaranteed to reach the supremum?
That's the million-dollar question, and actually one that the paper leaves open.
Okay.
Nobody's been able to prove if the supremum is achievable even with these complex distributions.
So mathematicians will be thinking about this for a while.
I think so, yeah.
Okay, so we've been talking about maximizing the casino's advantage.
Right?
What about designing games that are actually fair, where both sides have an equal chance of winning? Is that even possible?
That's a fantastic question. And it leads to one of the most intriguing parts of this paper.
Okay.
Remember that inequality, the one with x1 plus x2 plus x3 less than 2x4.
Yes, the one where we haven't found the exact maximum probability yet.
Right. What if we tweak that inequality a bit? Instead of 2x4, let's replace the 2 with a different constant, something between 2 and 3. We'll call it C star.
Okay, so we're changing the weighting of that fourth variable.
Yeah, essentially.
Okay, I'm curious where this is going.
So the question now is, can we find a value for C star that would make the game perfectly fair?
So we're looking for that Goldilocks value,
Exactly.
where the inequality is balanced to create a fair game.
Exactly. And the paper presents this as problem 5.3, which is like a call to action for mathematicians.
Go solve this.
Exactly. And it's not an easy problem. Finding that balance point for C star requires a deep understanding of how probability distributions and these inequalities and scaling factors interact.
So mathematicians around the world are working on this right now,
I would imagine so, yeah.
trying to crack this code.
And what makes it even more challenging is the paper gives very few hints about where to start.
Okay, so it's a real test
Yeah.
of mathematical ingenuity.
It really is, yeah. I mean, this paper, it's not just about providing answers.
Right.
It's about asking the right questions.
This whole conversation has really shifted my perspective on math. It's not just about formulas.
Yeah.
It's about asking deep questions.
Absolutely.
Exploring these complex ideas.
Yeah.
I'm eager to see what other insights this paper has. What else is on this mathematical map?
So we've been exploring, the theoretical side of all this, but
Yeah.
let's bring it back to the casino.
Okay.
I think this will make it even more interesting.
All right, I'm ready.
Imagine a casino, right?
Mm-hmm.
They want to offer beat the average, but with a twist. Instead of providing the dice,
Uh-huh.
they let the player bring their own.
Wait, seriously?
You can choose any number of sides, any distribution you like.
So I can bring my own loaded dice?
You can?
That sounds like the player has a huge advantage.
It seems that way, right?
Yeah.
You might think you can outsmart the casino.
Right.
But remember that limitation.
Ah, yeah.
No discrete die can achieve that perfect 2/3 probability.
It always comes back.
It always comes back to get you.
So even though they're giving me this freedom,
Yeah.
they still have an edge.
The casino's essentially saying, go ahead, try your best. We're confident the math is on our side.
It's like a mind game.
It is, yeah. It creates this illusion of choice, but they maintain that long-term advantage.
They're playing on a different level.
Yeah, they're using math as their weapon.
How would this play out in a real casino?
That's a good question. In the short term, some players might get lucky,
Right,
win a few rounds,
Yeah.
think they've cracked the code.
right.
But over time, that mathematical reality would set in.
Yeah, the house always wins.
The house always wins, exactly. It's a good reminder that sometimes our intuition about probability can be wrong.
Yeah, we think we have a good chance, but the math tells a different story.
Exactly. That's why this paper is so cool, right?
Yeah,
It gives us the tools to analyze these situations more deeply.
like a decoder ring.
Yeah, to see beyond our intuition to the truth.
You know, at the beginning, I was a little intimidated by this paper.
Yeah.
But honestly, this has been one of the most fascinating conversations.
It's been a pleasure, and this is just the tip of the iceberg, really. There's so much more to discover in the world of probability.
I'm feeling very inspired to keep learning.
That's the spirit. Who knows what mathematical treasures are out there?
Maybe one of our listeners will solve problem 5.3.
Yeah, maybe they'll figure out how to design those truly fair games.
That would be amazing.
It would, wouldn't it? Until then, keep those mathematical minds engaged
Absolutely.
and keep exploring the fascinating world around us.
I love it. Thanks for joining me.
Thanks for having me.
Welcome to another deep dive. We got an interesting paper this week by Bellec and Fritz about maximizing probabilities with independent and identically distributed random variables.
Yeah, it uses a game, the Beat the Average game, with dice and cards.
That sounds fun.
Yeah, to really dive into some pretty heavy math.
So let's start with that game. 3 of the same dice get rolled. You pick one, and if yours is at least the average of the other 2, you win.
Sounds fair, right? Like a 50-50 shot.
Right.
Well, that's where intuition can sometimes,
Lead you astray?
Exactly. The paper shows that by messing with the dice a bit, a casino can tilt the odds in their favor. It's all about how the values on the dice are spread out.
So how do they show this? Do they start with, like, what we expect from normal fair dice?
Yeah, they start with that baseline, then they do something clever. They reframe the whole thing as a card game.
Ooh.
Think of it as a deck of cards with values 1, 2, 4, all the way up to, well, 2 to the power minus 1, where m is how many cards you've got.
Okay, so how does a card game help us understand rigged dice?
It's a key step, because what they prove is that in this card game, the most the casino can win, no matter how big the deck, is 2/3 of the time.
2/3. Interesting. So that's like their ceiling.
Yeah, the ceiling for their advantage.
Right.
And then they show that with dice, by carefully choosing what numbers are on them, a casino can get really close to that 2/3 win rate.
Oh, so that's how the skewed values come in.
Exactly. That's the key.
Let's give an example, right? With the four-sided die?
Yeah, they use a four-sided die with the values 1, 2, 4, and 8.
Okay, I'm picturing it. How does that give the casino an edge?
Imagine you roll 3 of those dice. If one lands on a 1, let's say, and the other's on 4 and 8, the average is 6.
Right, which means?
The casino wins automatically. It's all about making those high averages more likely.
So even though it seems counterintuitive, those specific values create this kind of imbalance.
Exactly. And then the paper goes even further with what they call the bring your own die variation.
Okay, what's that?
The player gets to pick the die, but the way the payouts are set up, the casino still wins more often.
Ah, I see. So even with this illusion of choice,
The house still wins.
always wins.
It just goes to show even a simple game can have some pretty deep math hiding underneath.
Yeah, some hidden wrinkles. But the paper doesn't stop there, does it?
Nope. It takes this idea and says, hey, this is actually part of a much bigger problem. The problem of maximizing the expected value of a function using probability measures with this form, which essentially means looking at sets of these independent and eidetically distributed random variables.
Okay, can you break that down? That sounds pretty abstract.
Think of it like this. They've created a mathematical framework to analyze tons of situations where you have sets of random variables all following the same probability distribution. The beat the average game is just one example.
Ah, okay. So they're expanding on what they learned from the game, but applying it to a much wider range of problems.
Exactly. And one of the things they focus on is dealing with strict inequalities.
Strict inequalities,
Right.
meaning what exactly?
They're interested in maximizing the probability that a specific combination of these variables is strictly greater than 0. Using a strict inequality is important. Otherwise, you could just have everything equal 0, and the probability would be 1, trivially.
Right, that makes sense.
And one specific problem they dive into is this. The probability that the sum of the first 3 variables is less than twice the 4th variable. Written mathematically as 0.4 x1 plus x2 plus x3 to x4. They don't know the exact value for this supremum probability, but they give both upper and lower bounds for it.
So what are those bounds?
0.4 and 0.422. And to get that lower bound, they construct a very specific discrete probability measure. It assigns a probability of 12 to the value 0, and the other half is spread evenly among n distinct values between 0 and 1.
So they're really carefully arranging this distribution.
Yes, to make that inequality more likely to hold true.
And as n gets larger, this lower bound creeps closer to 25.
Exactly. The more they divide that remaining probability mass, the closer they get.
Impressive. So what about that upper bound? How did they come up with 0.422?
Well, that's where they bring in some serious computational power. They use 2 mixed integer linear programs, MILPs for short, to analyze all the different versions of that inequality, playing with how the variables are arranged.
MILPs. Could you maybe explain those a little more simply?
Imagine you're trying to find the biggest group of people who all fit specific criteria, like height, weight, and hair color.
Okay, I'm picturing it.
A MILP is a sophisticated algorithm that can solve problems like that, finding the best solution within those limits.
So they're using these MILPs to sift through all those possible combinations of inequalities.
Yes, to find the biggest set that can all be true at the same time.
Okay, so they get that upper bound of 0.422 from these MILPs. It's amazing how they blend theory with computation.
It's a powerful combo. And the cool thing is, the solution from the first MILP hints at a pattern that looks a lot like the distribution they used for the lower bound. So now there's this exciting conjecture. Could that lower bound, 0.4, actually be the true supremum probability?
That's a great question.
Yeah.
But before we dive into that, maybe let's rewind a bit and unpack that lower bound proof in more detail. It seems like there's some clever math at play there that's worth exploring.
All right, let's break down that lower bound proof. Essentially, they're trying to show that for any teeny tiny positive number, epsilon. You can find the special way to distribute probabilities, a discrete measure, let's call it nu, on the interval from 0 to 1.
Right.
Where the probability of our inequality that sum of the first three variables being less than twice the fourth is at least 2/5 minus that tiny epsilon.
Exactly, which basically establishes 0.4 as the lower bound.
Okay, got it.
So they start by introducing this positive integer n that's going to be important in defining our probability measure.
Right.
And then they construct this measure called, it assigns probabilities to specific values. Here, puts a probability of 1/2 at 0.
Okay.
And the remaining half is spread out equally among n different values between 0 and 1.
So they're kind of front-loading the probability at 0 and then carefully placing the rest. Yeah. And these n values aren't just random. They're chosen to be of the form 1 minus 2 to the power of negative I, where I goes from 1 to n.
Interesting. A geometric pattern.
Exactly. And that pattern is key to making this whole thing work. So now they need to bound the probability of our inequality, x1 plus x2 plus x3, less than 2x4, from below.
Okay, so do they try to calculate it directly?
They're a bit more clever than that. They break down the probability into 4 different events.
Okay.
Each one contributes to the overall chance of the inequality being true. The first event is simple. All 4 variables equal 0.
Right, that would have a probability of 1/16, since each variable has 1/2 chance of being 0, and they're independent.
Exactly. Now, the second event gets a bit trickier.
Okay.
It's when 2 of the first 3 variables are 0, the third one is positive, and the fourth is also positive, but bigger than half of that third variable.
I see. So that arrangement automatically makes the inequality true.
Exactly. They're being sneaky, using the structure of the inequality to their advantage.
And they account for the different ways those 2 zeros can be placed among the first 3 variables.
Oh, yeah. They consider all 3 possible combinations. That's why there's a factor of 3 in the calculation.
Right, because of symmetry.
Yeah, so the probability of the second event becomes 3/16.
Okay, got it. So what's the third event?
Similar idea, but now only one of the first 3 variables is 0. The other 2 are positive.
Okay.
And the fourth variable is positive too, but we need the sum of those 2 positive variables in the first 3 to be less than twice the fourth.
All right, that sounds a lot more complicated to figure out.
It is, but they use conditional probability to break it down. They separate the probability of the first 3 variables having that specific pattern of 1, 0, and 2 positive values, and then the probability of the sum of those 2 positives being less than twice the fourth, given that they are indeed positive.
So break it into smaller pieces.
Exactly. And to handle that conditional probability, they rely on how our probability measure is set up. Since x2, x3, and x4 are positive, they have to be from that set of n values we defined earlier, those 1 minus 1 over 2 to the I values.
Right.
And then a key observation, if x3 is strictly less than x4, then x2 plus x3 will automatically be less than twice x4.
So another condition that guarantees our inequality works.
Exactly. And to determine the probability of x2, x3, and x4 being different, given they're all positive, they use combinatorics, counting how many distinct triplets you can make from those n values.
They really are pulling out all the math tricks. What's the result of all this for the third event?
By putting all the pieces together, they establish a lower bound for the probability of the inequality. This bound depends on n, and as n goes towards infinity, the bound approaches 3/8.
So increasing those distinct values pushes the bound closer to 3/8. But they do even better than that, don't they, to get to that 2/5?
They do. To reach that 2/5 lower bound, they apply proposition 3.4 from the paper, which says that for any measure and a tiny positive epsilon, you can build a new measure nu on 0 to 1, such that the probability of our inequality under nu is greater than or equal to the probability under nu, divided by 1 minus the probability that the sum of the first 3 equals twice the fourth under hone, and then minus that epsilon.
Okay, I think I follow. It's like a probability amplifier.
Yeah, exactly. They're taking the existing probability and boosting it.
So how do they apply this to our situation?
They use that measure we've been working with where n goes to infinity and set epsilon to 0.
Right.
This gives a lower bound of 3/8 divided by 1 minus 1/16, which simplifies to 2/5, or 0.4. That completes the proof of proposition 4.1 and establishes the lower bound.
Wow, quite a journey. So carefully crafted probability distributions can really shift the outcomes?
They sure can. Now let's switch gears and look at that 0.422 upper bound. This is where those milpies come in.
Right, let's hear about those.
So remember, we're dealing with that inequality x1 plus x2 plus x3 less than 2x4. They realized that for any given number of variables, there are tons of different ways to arrange them within that inequality.
Like exploring all the different permutations.
Exactly. For example, with 6 variables, there are 60 different versions of that inequality.
Wow.
But they made a crucial observation. If you arrange those variables in ascending order, some versions of the inequality just can't be true.
So they can eliminate a bunch of them right off the bat.
Exactly. They're shrinking the problem, so to speak. Now, for smaller values, like 4 or 6, you could analyze the remaining inequalities by hand and find the biggest set that can all work together.
Right.
But as Manx gets larger, that manual approach becomes impossible. Too much computation.
And that's where the milpies come in.
Right. But how do you translate this problem of finding the biggest set of inequalities that work into something a MILP can handle?
Yeah, it seems like a big leap.
They cleverly reframe the problem as an optimization task. The goal is to maximize the number of inequalities that are satisfied.
Okay.
They use binary variables, which can only be 0 or 1, to represent whether each inequality is satisfied or not. And then they add constraints that capture the relationships between these variables, making sure only valid sets of inequalities are considered.
It's like speaking the milpies language.
Exactly. Now, they start with our original inequality, ci plus xj plus xk less than 2 for all I, but they introduce this small positive threshold.
A threshold.
Yeah, they subtract it from the right-hand side. It's needed for numerical stability in the solver, since strict inequalities can cause issues.
Makes sense, like a little tweak to make the problem more manageable.
Exactly. And then they use something called the Big M method to further translate these relaxed inequalities into linear constraints, something the MILP can understand.
Okay, I'm getting a sense of how complex this is. So they feed all of this into the MILP solver.
Exactly. And in their case, they use Gurobi. This solver then searches for the optimal solution, the biggest set of inequalities that can all be true.
And this gives them the upper bound.
Right. For example, for M15, the MILP gave an upper bound of 2304 divided by 5460, which is about 0.422. But because of that little threshold we added earlier, this bound isn't completely rigorous yet.
So they need to double check it.
Exactly. And for that, they use a second MILP.
Okay.
This second one aims to formally verify if the set of inequalities found by the first MILP is truly the biggest possible. It does this by trying to create disjoint subsystems of inequalities, meaning they don't share any inequalities where each subsystem is impossible to satisfy on its own.
It's like breaking the problem into smaller chunks and showing none of those chunks can completely work.
Exactly. The second MILP focuses on those inequalities that were satisfied by the first MILP and tries to group them into these impossible subsystems.
So if this second MILP defines a solution, it means they've confirmed the upper bound from the first MILP.
Precisely. And for M15, it did find a solution, verifying that 0.422 upper bound. This makes their findings even stronger.
Amazing. So much computational power combined with clever math.
Right.
But there's one more thing, right? About the solution from the first MILP.
Yes. For M15, the solution shows a pattern that's really similar to that probability distribution they used for the lower bound. It's like the computational solution is hinting at some deeper math underlying the problem.
Wow. Suggesting that the lower bound might actually be the real deal, the true supremum.
Exactly. A very intriguing development. And we'll delve into that conjecture and some other open questions in the next part of our deep dive.
So we have this lower bound and this upper bound, but you're saying there's more to the story. What else did Bellec and Fritz find?
Well, they go on to explore these really interesting open questions and conjectures based on their results. One that really grabbed my attention was what they call the 2/5 conjecture.
Okay.
They basically ask, is 2/5 the absolute highest probability you can get, the supremum for that inequality?
It's a bold statement, considering they only proved it as a lower bound. What makes them think 2/5 might be the true supremum?
Remember those MIL-PIT calculations? How for M15, the solution had this pattern that was so similar to the distribution that gave us the 2/5 lower bound.
Right.
It's like the computer is hinting that there's something special about that 2/5 value.
Yeah, that it's not just some random number, but the actual limit.
Exactly. It's fascinating how the computational stuff seems to echo the theoretical stuff.
It is. But how would you even prove or disprove that conjecture? Would you need even more powerful computers to push those MILPs further?
More power might get the upper bound closer to 2/5, but it wouldn't give us a definitive answer. For that, you'd need some new mathematical insight, maybe a whole new approach.
What kind of approach? Do they offer any ideas?
They suggest looking deeper into the properties of probability distributions,
Okay.
or finding new ways to exploit symmetries in the problem. It's a challenge to mathematicians, an invitation to explore these inequalities and see what's hiding there.
That's what makes math research so cool, right? The unsolved
Okay.
problems, the intriguing conjectures. It's all very exciting.
Totally. And this paper goes beyond that specific conjecture. It raises a broader question about attainability.
Attainability. Remind me what that means in this context.
It's about whether that supremum probability can actually be achieved with some specific distribution, or is it just a theoretical limit that you can get close to but never actually reach? Like
Yes.
knowing a place exists versus having directions to get there.
Right.
And they do have some thoughts on this. They argue that if a probability distribution has an atom at zero,
Me.
meaning it assigns some non-zero probability to zero itself, then it can't be the optimal one.
Wait, wouldn't having some weight at zero make the inequality more likely?
Mm-hmm.
Because those first three variables would have a higher chance of being small.
It seems that way, but they show that you can always shift that probability mass slightly away from zero and actually improve the overall probability of the inequality. It's not the most efficient way to maximize the chances.
So any contender for the optimal distribution has to spread things out a bit more strategically.
Exactly. They also argue that a distribution with only a finite number of support points can't be optimal either.
So it needs infinite support points.
It seems so. Carefully arranged to maximize the probability of our inequality.
Wow. It's like our math journey is taking us to these increasingly intricate places. You wonder if there's a trade-off between how simple the question is and how complex the answer turns out to be.
It's a fascinating thought, and there's one more interesting direction they point to. The idea of fair games in this framework.
Going back to that beat the average game where the casino had the edge.
Yeah. The question is, can we make it fair?
Level the playing field.
Exactly. They suggest searching for a specific coefficient,
Right.
which they call C star. That would make the inequality x1 plus x2 plus x3 less than C star times x4, a 50-50 proposition. So both
Right.
the player and the casino have an equal chance of winning.
So instead of that fixed 2 coefficient we were using before,
Right.
we're looking for the magic number that balances things out.
Exactly. And they even give us a range to explore, suggesting that C star might be somewhere between 2 and 3.
So finding that precise value, it wouldn't just create a fair game.
It might also tell us more about how these arid variables behave and how the probabilities of these inequalities work.
It's incredible how this game that seems so simple at first has led us to all these deep questions about probability.
I know, right? About theoretical limits and finding balance in mathematical equations.
That's the beauty of this paper. It takes a playful idea and uses it to explore a rich world of math. It leaves us with more questions than answers, but that's often how the best research works.
It does. It sparks curiosity
Yeah.
and challenges what we think we know.
Makes you want to dive in and learn more.
So listeners, we encourage you to think about these open questions. Maybe you'll be the one to find that C-star value or prove the 2/5 conjecture. The world of math is full of mysteries waiting to be solved. Until next time, keep exploring, keep questioning, and keep diving deep.
Welcome to another deep dive. We're tackling a question today that sounds super simple on the surface, but trust me, it goes way deeper than you might think. Can you really beat the average? We're diving into a paper to find out, and it's got some pretty surprising answers.
Oh, yeah, this one is a fun one. The paper is by Pierre Bellec and Tobias Fritz. It's called Optimizing over Eid Distributions and the Beat the Average Game.
So before we get into the nitty-gritty, let's set the stage for our listeners. The game is called, you guessed it, Beat the Average. You win if your die roll is higher than the average of 2 other dice. Sounds pretty straightforward, right? Like almost like a 50-50 kind of thing.
You'd think so, right? 3 dice, all fair, just a roll of the dice, as they say. But that's where this paper really gets interesting. It shows how this seemingly fair game can be totally skewed. Well, if you get to design the dice. We're not talking about your typical 6-sided ones anymore.
Okay, so we're moving beyond the standard dice. Where do we even begin with non-standard dice? Like, how many sides are we talking?
Well, the paper uses a simple example to illustrate this, just a 2-sided die.
2-sided, so like a coin flip, basically.
Exactly. It can land on either a 0 or a 1. Let's say the probability of rolling a 1 is P. Now imagine you're the casino. You win if the players die, let's call it die A, rolls a 0, and at least one of the other 2 dice, let's call them B and C, rolls a 1.
All right, so we're already thinking like the house, trying to figure out how to make this game work in our favor.
Right. And if you work out the probabilities, the chance of the casino winning is 1p times 1p squared, which simplifies to, well, it simplifies to a cubic equation.
A cubic equation. Okay, so already getting a little more complex than just flipping a coin.
It's p cubed minus 3p squared plus 2p.
So even with this super basic two-sided die, the casino can tweak the odds just by messing with that probability, p, the chance of rolling a 1.
Exactly. Now, let's crank up the complexity a notch. The paper introduces a card game version of Beat the Average.
Okay, so switching gears from dice to cards, but same basic idea, right? Highest card beats the average.
Yep, same rules.
But here's where it gets kind of wild. The casino can always guarantee a win in this card version. Doesn't matter how many cards are in the deck.
Always. Wait, so there's zero chance for the player to win? How is that even possible?
That's what's so cool about this paper. It reveals these hidden mathematical tricks. The casino pulls this off by carefully picking the values on the cards. They use a sequence of 1, 2, 4, and so on, all the powers of 2, up to 2 to the power of m1, where num is how many cards are in the deck.
So the values on the cards are the key. It's like a magic trick, you know? You think you have a chance, but the math is completely stacked against you.
Yeah, and the paper proves this using a really clever technique. They analyze what happens when you shrink the deck down to just 3 cards. It simplifies things so you can really see the core advantage the casino has. Then they show how it holds true no matter how many cards you add back in.
Okay, I'm starting to see how this card game is more than just a fun side note. It sounds like it's the key to understanding how the casino can rig the dice game, too. You got it. They take what they learned from the card game and apply it to the dice, and bam! The answer to our original question is yes. Absolutely, the casino can rig the dice game, too.
So it's not just bad luck at play here. The dice themselves could be working against you, like loaded dice, but in a much more subtle way.
It's all about the numbers on those dice. If the casino picks values that mimic that winning sequence from the card game, 1, 2, 4, 8, and so on, they shift the odds big time.
I'm starting to rethink every dice game I've ever played.
And they don't stop there. Theorem 1.5 in the paper shows that with the right set of numbers on the dice, the casino can get crazy close to a 23 winning probability. Like, they're practically guaranteed to win in the long run.
So there's a limit, 23, but they can get as close to that as they want.
Exactly. And what's really interesting is this 23 limit, it's not just about dice. It pops up in any situation where you're trying to beat the average using independent and identically distributed random variables. That's a mouthful, but it basically means things that are random and follow the same probability distribution.
So we've gone from a simple game of dice to, like, a universal truth about probability and averages.
Exactly. It's like the authors are using this game as a starting point to explore some really deep mathematical concepts. They formalize this idea with something called Problem 2.1.
Problem 2.1, all right. Lay it on me.
It looks like kind of intimidating at first, all these symbols and stuff, but what it's really asking is, how can we maximize the expected value of a function, the average outcome, when we're dealing with these random variables that are all independent and come from the same distribution?
So it's bigger than just beating the average in one game.
Yeah.
It's about understanding the limits of what you could do with probability in general.
Exactly. And Theorem 2.4, that's a big one here. It dives into what happens when you take more and more samples, or in our case, roll more and more dice. And it basically says there's a limit, a ceiling, to how much the casino can win. And the more you play, the more you can see that limit taking shape.
Okay, so the more data we have, the clearer the boundaries of the game become.
Right. Now, I want to talk about something that gets particularly tricky.
Let's hear it.
Okay. It's the problem of maximizing the probability of a strict inequality. When we're dealing with a greater than sign instead of a greater than or equal to.
Why does that one little symbol make such a big difference?
Because it throws out all those easy solutions where everything's equal. Like if you have greater than or equal to, everyone just rolls the same number, you're good. But with just greater than, you got to get more creative.
It's like that strictly part forces us to find a more subtle way to play the game.
Exactly. And they point out that for this problem to even be interesting, the sum of those coefficients, those constants in the inequality, has got to be less than or equal to 0. Otherwise, it's too easy to win. You just set everything to be positive and you're done.
It's like they're setting up the rules of the game to make it a real mathematical puzzle.
Right. Now, here's where they get really clever. They use something called perturbation to tackle these strict inequality problems.
Perturbation sounds intense. Break that down for me.
Okay, imagine you're trying to balance a pencil straight up on its tip. Super hard, right? Almost impossible. But if you give it a tiny little nudge, a controlled shake, sometimes that actually helps it stay balanced.
So we're talking about adding a little bit of randomness, like a calculated shake of the dice?
Yep. They add a little random noise to the random variables. And the crazy thing is, if you pick the right kind of noise, you can actually boost the probability of winning, of satisfying that inequality.
Wait, so they're not just playing with the numbers themselves, they're messing with the randomness itself.
Right. They're like packing probability. And they take this even further with what they call an iterative process.
So they do this perturbation thing multiple times, like a series of little shakes.
Exactly. They start with the original random variables, and then they keep adding these little bits of noise, each time drawing from the same special noise distribution.
It's like they're fine-tuning the randomness step by step.
Exactly. It's really cool, and they prove that this approach can always find a better solution. No matter how good your current probability distribution is, you can always find another one using this method that gives you an even better chance of winning.
Okay, so this is going way beyond just beating the average in a simple game, right? They're exploring some really fundamental stuff about probability itself.
Yep, and in the next part of our deep dive, we're going to see how they put all this to the test with an even tougher example, one that's even harder than the original Beat the Average game.
Sounds like things are about to get even more interesting.
Welcome back! We're continuing our deep dive into Beat the Average and how this simple game leads to some serious math. Last time, we saw how the casino could stack the deck in, both the dice and card versions, and now we're going to get into the nitty-gritty of how they prove that, mathematically speaking.
Yeah, that card game was a real head-scratcher. The casino could always win just by choosing the right values on the cards. I remember it was all about powers of 2, right? 1, 2, 4, and so on.
Exactly, and it all boils down to Proposition 1.4 in the paper. It shows mathematically that no matter how many cards are in the deck, the best the casino can do is win 23 of the time.
Okay, 23. But how do they actually prove that? Like, how do you even start to prove something like that?
Well, the proof has two main parts. First, they show that, this power of 2 sequence, it really does give the casino that 23 winning probability. They do this by focusing on a specific inequality. 2A is less than B plus C. A is the player's card, B and C are the casino's cards.
Okay, so 2A less than B plus C. Got it.
The key thing is, with those power of 2 values, that inequality is only true if A is smaller than both B and C.
Oh, I see. If A is the smallest card, then doubling it is always going to be less than adding up the other two.
You got it. Now think about any 3 cards from the deck. There are only 6 ways you can arrange them, right? And in 4 of those arrangements, A will be the smallest.
Right. So for any 3 cards, the casino has a 4 out of 6 chance of winning.
And that, my friend, is exactly 23.
Okay, that makes sense for 3 cards. But what if there are more cards? Could the casino do even better than 23 with some other clever sequence?
Great question, and that's where the second part of the proof gets super interesting. It uses something called the probabilistic method.
The probabilistic method sounds fancy.
It's a way of proving that something exists, even if you can't actually point to it, like construct it directly. In this case, they start with a deck of, say, cards.
Okay, 1 cards.
Now, pick any 3 cards randomly from that deck. We already know that for those 3, the casino's winning probability can't be more than 23, right?
Yeah, we just proved that.
Well, we picked those 3 cards randomly. So that means the overall winning probability for the whole deck, it's got to be the average of the winning probabilities for all possible groups of 3 cards.
Right, so if none of those individual probabilities can be bigger than 23, then the average can't be bigger either.
Exactly. We've essentially set a hard limit, a ceiling on how well the casino can do no matter how big the deck gets. Pretty neat, huh?
That's really clever. I like it. So we used randomness to prove something about, a deterministic probability.
It's a powerful tool, this probabilistic method. Now, the paper also gives another way to prove the same thing, using something called indicator functions.
Indicator functions. I think I vaguely remember those from the first part of our deep dive. But to be honest, I could use a refresher.
No problem. They're basically like switches. They're either on or off, 1 or 0, depending on whether a certain condition is true.
Got it. On or off, 1 or 0, like a light switch.
Exactly. So take a look at this equation. It's equation 1.4 from the paper. It says 3 times the probability that A is less than B plus C over 2, that's equal to the expected value of a bunch of these indicator functions all added up. And that whole thing is less than or equal to 2.
Whoa, okay, lots to unpack there. Let's start with those indicator functions. What exactly are they indicating?
Okay, each one checks if one of the players is beating the average. So like the first one, it's on if A is less than the average of B and C.
So if A is the smallest card, that function would be a 1, right? On.
Exactly. Now, because the problem is symmetrical, the average value of each of those indicator functions, it's got to be the same. That's why there's a 3 out front. It's because there are 3 of them.
Okay, makes sense. 3 players, 3 indicator functions.
Now, here's the key point. Only 2 of those inequalities can be true at the same time.
Right, because if all 3 were true, you'd end up with 0 being less than 0, which doesn't make sense.
Exactly. That's why the sum of those indicator functions, it can never be bigger than 2. That's why we have that less than or equal to 2 on the right side of the equation. And if you divide both sides by 3, what do you get?
23. There it is again.
Exactly. It's another way of showing that 23 is the absolute best the casino can do.
Okay, I'm starting to really appreciate how these proofs work. It's like, with a little bit of logic, you can uncover these hidden truths about probability.
And now, let's bring it back to the dice. Remember Theorem 1.5? It shows that, yeah, the casino can rig the dice game too. And they can get as close as they want to that same 23 winning probability.
I remember they were using dice values that match the winning card sequence. 1, 2, 4, 8, like that.
Right. So imagine you make a die with, say, M sides, and each side corresponds to one of those winning card values.
Okay, both sides.
Now we roll 3 of these dice and make sure they all land on different sides.
So it's like we're playing the card game, but with dice instead.
Exactly. And what they show is the probability of losing in this scenario, it's the same as the probability of losing in the card game. They use some fancy notation here, random variables and stopping times, but the basic idea is to connect those 2 versions of the game.
So they're linking the dice game and the card game mathematically to show that the same principles apply.
Exactly. And by doing this, they come up with a lower bound for how well the casino can do with dice. It's 23 minus 3 over M.
Okay, 23 minus 3 over M. So as M gets bigger, as we add more sides to the dice, that 3 over M part gets smaller and smaller.
Right, which means the casino's winning probability gets closer and closer to 23.
So in theory, they could get really close to that 23 limit just by using dice with enough sides.
Exactly. And they also use that inequality we talked about earlier, inequality 1.4, to prove that 23 is a hard limit. No matter what values you put on the dice, as long as the rolls are random and independent, you can't do better than 23.
So that 23, it's a universal limit, a mathematical truth. Kind of comforting to know, in a way.
It is, but there's a little catch, a subtlety that they point out in the non-achievability part of the theorem. They say you can never actually reach that 23 limit perfectly with dice.
Wait, so you can get infinitely close but never quite hit it. Why not?
It's because dice are discrete. You have a fixed number of sides, a fixed number of outcomes. To get exactly 23, you'd need a continuous distribution where the probabilities can vary smoothly over an infinite number of values.
Ah. So it's like a theoretical limit, but in practice, you can only approach it, never actually reach it.
Exactly. And that leads to a really interesting twist, what they call the bring your own die game.
Bring your own die. What's that all about?
It's where the player gets to choose their own die. Seems like they have the advantage, right? But the casino still wins because they know that 23 is impossible to achieve perfectly.
It's like a mathematical sleight of hand. The player thinks they have the power, but the underlying math is always working in the casino's favor.
Now let's zoom out a bit. The paper takes what we've learned about beat the average and applies it to a broader class of problems. They call it optimizing expectations over 8 distributions.
Optimizing expectations. Okay, break that down for me.
It's basically about finding the best possible average outcome, the maximum expectation, when you're dealing with a bunch of random variables that are all independent and follow the same distribution.
So it's not just about beating the average in a game anymore. It's about understanding the limits of what you can expect in any probabilistic system.
Exactly. And to make things a bit easier to handle, they introduce a shorthand notation for averaging over finite sets. They use the integral symbol, which is kind of like summing things up, but in a more continuous way.
Anything to simplify the math is welcome in my book.
Right. Now, a key result here is lemma 2.3. It provides an upper bound, a ceiling, for that maximum expectation we're trying to find. It says, okay, if you have n random variables and you pick any number that's bigger than or equal to n, then the best you can do is limited by this average value calculated over all possible injections from a set of n elements to a set of m elements.
Whoa, injections. I remember those from earlier, but remind me, what are they again?
Imagine you're assigning players to positions on a team. Each player gets one spot, no sharing. That's what an injection does. It maps each element from one set to a unique element in another set.
Right, no overlaps. So in this case, each injection represents a way of assigning specific values to our random variables.
You got it. And by averaging the function over all those possible assignments, we get an upper limit on how high that average can go.
So we're essentially trying out all the combinations, all the possible ways those random variables can shake out, and seeing what the best possible average outcome is.
Exactly. And the proof of this lemma, it hinges on a really important property of these ATN random variables: exchangeability.
Exchangeability. Sounds important.
It means you can swap the positions of those variables, and it doesn't change the overall probability.
Oh, right. It doesn't matter which specific variable gets which index.
Yeah.
Because they're all coming from the same distribution. They're interchangeable.
Precisely. And that's a key insight that allows them to prove this upper bound. Now, Theorem 2.4 takes this a step further. It says, as that number grows towards infinity, as we consider more and more possible assignments, the upper bound we get from lemma 2.3, it actually converges to the true maximum expectation.
So the more possibilities we consider, the more accurate our estimate of that maximum average value becomes.
Exactly. The proof uses some calculus and probability tricks, but the basic idea is that an average can never be bigger than the biggest thing you're averaging.
Makes sense. So we're essentially squeezing that maximum expectation value between an upper and a lower bound.
And remark 2.5 gives us even more information. It says, not only do these upper bounds converge, but we also know how far off we are at each step. It's like having a speedometer telling us how fast we're approaching the finish line.
So it's not just blind convergence. We actually know how quickly we're getting there.
Right. And in the next part of our deep dive, we'll see how all of this comes together to tackle those tricky, strict inequalities using that clever perturbation technique we discussed earlier. Stay tuned.
Welcome back for the final part of our deep dive. We've been exploring Beat the Average, and I have to say, this paper has taken us on quite a mathematical journey.
Yeah, we've gone from simple dice rolls to some pretty deep concepts in probability and game theory.
Last time, we saw how the casino could rig the game in their favor. And we even touched on this broader idea of optimizing expectations, finding the best possible average outcome.
Right. And now it's time to tackle what I think is the most mind-bending part of this paper: maximizing the probability of a strict inequality.
Strict inequality. So we're talking about a greater than sign, no equals allowed.
Exactly. And that little detail makes a huge difference. It forces us to find more subtle, more creative solutions.
We talked earlier about how it rules out those easy wins where everyone just rolls the same number.
Right. And the paper dives deep into this in section 3. They focus on this inequality. It's a summation. It's the sum of C sub n times x sub I. All that's got to be greater than 0.
Okay, C sub I and x sub I, those are the constants and the random variables, right?
You got it. So the challenge is, what probability distribution gives you the best chance of making that inequality true?
And they point out that for this problem to be interesting, the sum of those constants, those C sub I values, has got to be less than or equal to 0.
Right. Otherwise, it's too easy. You just make all the random variables positive and boom, you win every time.
So they're setting up the rules of the game to make it a real challenge.
Exactly. And to get a handle on this, they use a result we talked about earlier, lemma 2.3. Remember that one? It gives us an upper bound on how well we can do.
Yeah, I remember. It was all about injections, those one-to-one mappings.
Right. So we pick a number m bigger than or equal to n, which is the number of random variables we have.
Okay, m and n.
Then we look at all the possible ways to map those n random variables to m-specific values. And lemma 2.3 tells us that the best possible probability of winning, of making that inequality true, is limited by how many of those mappings actually work.
So we're basically trying out every possible scenario, every combination of values, and seeing how often we win.
Exactly. It's like a massive simulation. The only problem is actually calculating this upper bound. It can be a real pain. It's a computationally hard problem.
So we might not always be able to get an exact answer easily.
Right. But there might be cases where we can exploit some special structure, some pattern in the problem to make it easier.
So it's a challenge, but not necessarily impossible.
And remember, remark 2.5. That gives us a way to find lower bounds so we can at least get a sense of how well we might be able to do.
Yeah, it was about constructing specific probability distributions.
Right. They do this by using a uniform distribution over a carefully chosen set of values. It's like creating a fair lottery, where each of those values has an equal chance of being kicked.
So we have tools for finding both upper and lower bounds, which means we can narrow down the range where the true answer must lie.
Exactly. Now, here's where things get super interesting. They introduce a technique called perturbation.
Perturbation. I'm intrigued. I remember you mentioned it earlier about adding a little bit of randomness.
Right. It's like giving those random variables a little nudge, a little shake, and if you do it just right, you can actually improve your chances of winning, of making that inequality true.
It's like you're manipulating probability itself.
Yeah, and the heart of this technique is captured in equation 3.6. It shows that when you add this little bit of noise, the probability of winning is basically what it was before, plus an extra term.
An extra term. What's that all about?
It depends on two things. First, the probability that the original random variables add up to exactly 0.
Okay, so we're right on the edge there.
Right. And second, the probability that the noise itself satisfies the inequality. So the noise only comes into play when the original variables are kind of teetering, right on the verge of winning or losing.
It's like that tiny push that tips the scales in your favor.
Exactly. And they take this even further with an iterative process. They keep adding these little bits of noise, each time drawing from the same carefully chosen distribution.
So it's like a series of tiny adjustments, each one making the probability a little bit better.
Right. And Proposition 3.4 shows that this method can always find a better solution. No matter what probability distribution you start with, you can always find a better one using this technique.
So it's not just about finding a good answer. It's about constantly searching for an even better one.
Right. Now, in Section 4, they put all of this to the test with a really tough example. They look at this inequality, x1 plus x2 plus x3 less than 2 times x4, and they try to figure out the absolute best probability of making it true.
So they upped the ante. It's like the boss level of beat the average.
Exactly. And they managed to find both a lower bound and an upper bound for this probability. They say it's somewhere between 0.4 and 0.422.
So they've narrowed it down, but the exact answer is still a mystery.
Yeah. And the way they find that lower bound is really clever. They construct a specific probability distribution with these carefully placed atoms of probability. It's like they're building a probability distribution brick by brick, each brick perfectly placed to maximize that chance of winning.
It's like a work of art, a masterpiece of probability.
And for the upper bound, they bring out the heavy machinery. They use something called mixed integer linear programming, or MIL.
MIL-P. That's a mouthful.
It's basically a way of using computers to solve optimization problems.
So they're using every tool at their disposal to crack this problem.
Right. And even after all that, they still leave us with some tantalizing open questions like Conjecture 5.1. It claims that the best possible probability for that tough inequality, the one with 4 variables, is exactly 25.
So they're throwing down the gauntlet, challenging other mathematicians to prove or disprove it.
Exactly. And then there's the question of attainability. Can you actually find a real probability distribution that achieves that theoretical 25 limit?
It's a question about the very nature of probability, about whether we can actually reach those theoretical limits in practice.
And finally, they touch on the idea of fair games. Can we change the rules of the game, tweak those coefficients to make it truly fair so that no one has an advantage?
So it's not just about winning or losing. It's about finding that perfect balance, that mathematical sweet spot where everything is truly fair.
This paper started with a simple game, but it's taken us on an incredible journey exploring deep concepts in probability, game theory, and even the philosophy of mathematics.
It's a reminder that even the simplest questions can lead to profound discoveries, and that the world of math is full of surprises. If you're interested in learning more, we definitely recommend checking out the full paper. It's a fascinating read.
Absolutely. It's full of insights and challenges that will keep you thinking.
And on that note, we'll wrap up this deep dive. Thanks for joining us on this exploration of probability, game theory, and the surprising depths of beat the average. Welcome back, everyone, for another deep dive. Today, we're going to be looking at something that looks really simple at first glance. But we're going to show you how it hides some pretty deep mathematical ideas.
Okay.
It's this game called Beat the Average.
Okay.
So the way it works is you have 3 identical dice.
Okay.
They get rolled. You pick one of the dice, and you win if the one that you pick is at least as big as the average of the other 2.
Interesting.
Yeah. So at first glance, it seems pretty easy.
Yeah, it sounds pretty straightforward.
Yeah. but we're going to see if it really is that simple. Let's see what our expert has to say about it.
Well, I think one of the things to keep in mind is that casinos don't tend to offer games where the odds are stacked against them.
Right. That makes sense.
So as we kind of unpack this and delve into the mathematics behind it, we'll see that the key to this game lies in using non-standard dice.
Non-standard dice.
Mm-hmm.
Okay. So let's start with the familiar six-sided dice.
Okay.
The ones everyone's used to. It seems pretty symmetrical, and you'd think it'd be a pretty fair game, right?
Yeah, with standard dice, the odds are actually slightly in the player's favor.
Really?
Which, of course, wouldn't make much sense for a casino.
No, not at all.
That's where these non-standard dice come into play.
Right.
By changing the number of sides and the values on those sides, they can really manipulate the probabilities.
Okay. So let's get into these non-standard dice. What if we start with, like, the simplest case possible, like a one-sided die?
Well, a one-sided die is basically just a sphere.
Right. Yeah.
Every roll is going to be the same.
Yeah.
So you would just end up with a tie every time.
Yeah. It'd be a pretty boring game.
Not much of a casino game.
Definitely not.
Oh.
Okay. So one-sided dice are out. How about we step it up to two-sided dice?
Okay.
So for this, we can assign the values 0 and 1,
Okay.
each with a probability P of landing on 1.
Yeah.
So now things should get a little more interesting.
Yeah. So in this scenario, for the casino to win your die, let's call it die A, would need to land on 0. And at least one of the other two dice, let's call them B and C, would have to land on 1.
Got it. So we need to figure out the probability of that happening.
Exactly. So let's break it down.
Okay.
The probability of A landing on 0 would be 1 minus P.
1 minus P. Right, because P is the probability of landing on 1.
Exactly. And then we need the probability of at least one of the other dice landing on 1.
So either B or C landing on 1.
Right, which is the same as 1 minus the probability of both of them landing on 0.
Okay, I'm following.
So that would be 1 minus P squared.
Okay.
You multiply that by the probability of A landing on 0, and you get the probability of the casino winning.
So that's 1 minus P times
1 minus
What?
1 minus P squared.
Exactly. And when you simplify that, you get an expression that's cubic in P.
Cubic, so like P cubed.
Yeah, it's P cubed minus 3P squared plus 2P.
Okay. And does that give the casino a winning edge?
Not really. Even if they try to optimize the value of P to maximize their chances of winning, their winning probability never gets higher than about 0.385. So even with two-sided dice, the casino can't quite tilt the odds in their favor.
That's right.
Okay. So let's try adding another side. What about three-sided dice? That should make things a bit more complex, right?
Absolutely. As you increase the number of sides, the potential outcomes grow really quickly.
Right.
Even small changes in the values on the dice can have a significant impact on the probabilities.
Okay. So, for example, let's say we have a three-sided die with the values 1, 2, and 4.
Okay.
And each side is equally likely to come up.
Yeah.
How would we analyze that?
Well, now you're talking about 27 possible combinations.
27.
Yeah. Because you have 3 dice each with 3 sides. So 3 times 3 times 3, that's 27.
Oh, right.
Right.
Okay. So with 27 combinations, that's going to be a bit more challenging to analyze.
It gets pretty complex.
But if we were to go through all those combinations and calculate the probabilities, what would we find?
You would find that the casino's winning probability increases to about 0.481.
0.481. So we're getting closer to breaking even.
Right. But they're still not guaranteed an advantage.
It seems like they're having a tough time finding that sweet spot.
It's a challenge for them. You see, they need to find the right combination of the number of sides and the values on those sides to tilt the odds in their favor.
Right.
But they also don't want to make it too obvious to the player.
It can't be too blatant.
Exactly. It has to look like a fair game.
So to kind of wrap our heads around this complexity, I think it would be helpful to consider a different version of beat the average.
Okay.
Instead of dice. Let's think about a card game.
A card game.
Yeah. Imagine we have a deck of cards, each with a unique value,
Okay.
and we play the same game. 3 cards are drawn. You pick one and you win if yours is greater than or equal to the average of the other 2.
Interesting. So it's the same concept, but with cards instead of dice.
Exactly. Why do you think this might be helpful?
Well, I think this card version is a good way to introduce a powerful mathematical tool called the probabilistic method.
The probabilistic method?
Yeah.
Okay, I'm not familiar with that. Can you
Yeah.
explain?
Yeah, so the probabilistic method is a way of proving the existence of something without actually having to construct it.
Okay. That sounds a bit abstract.
It is a bit abstract, but think of it this way. Imagine you're looking for a specific arrangement of cards in a deck.
Okay.
The probabilistic method wouldn't try to directly find that arrangement.
Okay.
Instead, it would prove that that arrangement exists by showing that there's a non-zero chance of getting it if you shuffle the deck randomly.
Oh, I see. So it's like saying, I might not know exactly how to make this happen, but I can prove that it's possible for it to happen.
Exactly. It's a way of demonstrating possibility without having to actually demonstrate the construction.
Okay. That's a really interesting concept. So how does that apply to this card game that we're talking about?
Well, we can actually use the probabilistic method to show that in this card version of Beat the Average, the casino can create a deck of cards that allows them to achieve a 23-win probability.
23? Wait, so that means they would win 2 out of every 3 games on average?
Exactly.
Wow. That seems like a pretty significant advantage.
It is, and the way they achieve this is by carefully selecting the values on the cards.
Okay, so how does that work? What kind of values would they use?
They would use a deck where the values double with each card. So like 1, 2, 4, 8, 16, and so on.
Okay, and how does that specific deck guarantee a 23 winning probability?
It's all about the relationships between the numbers. Let's take any 3 cards from this deck.
Okay.
We'll call them A, B, and C. A is your card.
Got it.
Now, for the casino to win, the following inequality needs to hold true. 2A has to be less than B plus C.
2A less than B plus C.
Okay, this is the same as saying that A is less than the smaller of B and C.
Right, because if A is less than the smaller of the 2, then it's definitely less than their average.
Exactly. And because of the way the values in this deck are structured, this inequality holds true for 4 out of the 6 possible arrangements of any 3 cards.
4 out of 6, which is 23.
Exactly.
That's pretty clever.
Yeah.
So they've rigged the card game in their favor. But can they do the same thing with the dice version?
That's a great question. And that's where things get even more interesting. We can think of the dice version of the game as a kind of limit of this card version.
A limit? What do you mean?
Imagine we take countless copies of this rigged deck of cards and combine them into one giant deck.
Okay.
It's like creating a die with a huge number of sides where each side represents a card from the deck.
So it's like a theoretical die with an almost infinite number of sides.
Exactly. And what this implies is that the casino can design a set of dice that will get them arbitrarily close to that 23 win rate that they achieve with the cards.
Wow. So even though the dice version seems fair at first glance, the casino can still manipulate the odds.
Right. They can't hit that 23 probability exactly with dice because the outcomes are discrete.
Discrete meaning?
Meaning they can only take on specific values. There are gaps between the possible outcomes.
Whereas with the cards, it's more of a continuous spectrum.
Exactly. And it's that continuity that allows them to hit that 23 probability precisely.
Okay. So even though they can't get to 23 exactly with dice, they can still get very close.
Yeah. Yes. And that 23 is actually the theoretical maximum that they can achieve.
Okay. And how do we know that's the maximum?
We can prove it using that same probabilistic method we talked about earlier.
Wow. So we've seen that a perfectly fair game where both sides have a 50-50 chance is impossible in the card version if the casino strategically chooses the deck.
Huh.
And it seems like this limitation carries over to the dice version as well.
That's right.
So what if the casino tried to introduce a different twist? What if they said you could bring your own die?
Bring your own die.
Yeah, you bring your own die to the casino, they roll it 3 times, and the same rules apply.
Okay.
Would that give the player an advantage?
That's a clever idea. It sounds like the player has all the power now.
Right, because they can choose any die they want.
But remember, we're talking about casinos here. There's always a catch.
So you're saying they still have an edge even in this bring your own die scenario?
Unfortunately, yes. Even if you bring your own die, the casino can still tilt the scales ever so slightly in their favor.
How is that possible? I thought the player was in control now.
It comes down to a fundamental difference between the card game and the dice game.
What difference?
It's the difference between continuous and discrete distributions. In the card game with a potentially unlimited deck, we can approach a continuous distribution.
Meaning there are no gaps between the possible values.
Exactly. But with dice, the outcomes are always discrete.
So no matter what die you bring, there are always going to be gaps between the possible outcomes.
Right. And it's those gaps that the casino can exploit.
Wow. So even when you think you've outfoxed the casino by bringing your own die, the math is still working against you.
It's a great example of how deeper mathematical principles can really underpin even seemingly simple games.
Yeah, it really highlights the distinction between continuous and discrete distributions and the implications they have for fairness in games of chance.
Exactly.
So this casino game has actually led us to a much broader mathematical landscape.
It has.
We've stumbled upon a specific instance of a more general problem, which is optimizing expectations over what are called IID distributions.
That's right. IID stands for independent and identically distributed.
So we've been focused on this one particular game, but the underlying math is much more general.
It is. We're essentially asking, given a certain function and a set of random variables, how can we adjust those variables to achieve the best possible average outcome?
Okay, so we're moving from a fun casino example to a more abstract mathematical problem.
Right.
Can you give us a sense of what this general problem looks like in mathematical terms?
Sure. Let's say we have a set of random variables, which we'll represent with the letter x.
Okay.
And we have a function that we want to optimize, which we'll represent with the letter f.
Okay.
What we're interested in is maximizing the expected value of this function applied to our random variables.
So maximizing the expected value of f of x1, x2, and so on up to xn.
Exactly. Where these she's are our IID random variables.
IID meaning?
Independent and identically distributed.
Yeah.
So basically, each random variable is drawn from the same distribution, and they don't influence each other.
Okay, I see. And by optimizing, we mean finding the best possible value for that expected value.
Precisely. We want to find the absolute best case scenario.
Got it. So how do we represent this idea of averaging over all possible combinations of our random variables?
Well, to represent averaging over finite sets, we can use a simple integral notation.
Integral notation.
Yeah, it's just a shorthand way of representing summation. So the integral of a function over a set basically means we're summing up the function's values at every point in that set and then dividing by the total number of points.
So it's like finding the average value of the function over that set.
Exactly.
And that notation helps us capture this idea of exploring all the possible combinations of our random variables and seeing what the average outcome is.
Precisely.
Okay, so we have our notation for averaging. Now, is there anything that tells us about the limits of what we can achieve?
Yes. There's a crucial result called lemma 2.3 in the paper we're looking at.
Lemma 2.3. And what does this lemma tell us?
It basically puts a cap on how high this expected value can go. It says that no matter what probability distribution we choose for our random variables, the maximum expected value is going to be bounded by the average of the function over a specific finite subset of points.
So it's like a ceiling on how good we can make things.
Mm.
No matter how clever we get with choosing our probabilities, there's a limit.
That's right.
And I'm guessing this limit depends on the specific function we're dealing with.
It does. And it also depends on how many random variables we have.
Okay, so we know there's a limit, but how do we find a distribution that gets us as close to that limit as possible?
That's the real challenge. And one approach that mathematicians use is to start with a simple distribution and then try to perturb it.
Perturb it.
Yeah. Basically shake things up a bit.
Okay.
The idea is to introduce a little bit of randomness into our variables.
So like adding some noise to the system.
Exactly. And then see if we can improve the expected value.
Interesting. So we're adding randomness to try to push things in the right direction?
Right. Now, there's a result in the paper called Proposition 3.4.
Proposition 3.4.
Okay. And this proposition tells us that this perturbation method can always find a distribution that's at least as good as the one we started with.
So we're guaranteed to either improve or at least not make things worse?
Right. But there's an interesting caveat to this proposition.
Oh, what's that?
It says that a distribution where all the probability is concentrated at 0 is never going to be optimal.
Why is that?
Well, if all of our random variables are fixed at 0, they can't really contribute to the function we're trying to maximize.
Right. They need some variation, some spread to have an impact.
Exactly. So we need to find a distribution that avoids putting all the probability at 0, but still allocates the probability strategically to other values to get us closer to that upper limit.
Okay, I see. So this leads us to a specific example that the paper explores.
Yes.
Which is this inequality, x1 plus x2 plus x3, is less than 2 times x4.
Right.
And the challenge here is to find the probability distribution that maximizes the chance of this inequality being true. And so far, they've found a lower bound.
Right. The lower bound they found is 25.
Which is 0.4.
Right.
But we know there's an upper bound as well.
We do. And narrowing that gap is where things get even more interesting.
It's like a mathematical treasure hunt.
It is. We're searching for that optimal distribution that gives us the highest possible probability.
And that's where we'll pick things up next time.
Sounds good.
Welcome back to our deep dive into Beat the Average. Last time we were talking about maximizing the probability of that inequality holding true x1 plus x2 plus x3 less than 2 times x4.
Yeah, we found a lower bound of 0.4, but the question is, can we get any closer to that upper limit?
Right. And you were about to tell us how you arrived at that lower bound.
Yeah, so remember we said that having all the probability concentrated at 0 is never optimal.
Yeah, because if all the variables are 0, there's no chance for the inequality to be true.
Exactly. So we started with a very simple distribution with an atom at 0.
Atom.
Yeah, it just means a point where the probability is not 0. And another atom at a value a little bit bigger than 0.
Okay.
And then we use proposition 3.4, that perturbation method, to shift the probability mass around.
So you're basically exploring different distributions to see if you can find one that gives you a higher probability.
Right. We experimented with adding more atoms, adjusting their positions, and tweaking the probabilities.
So it's like you're sculpting the distribution, looking for the shape that gives you the best chance of satisfying the inequality.
That's a good way to put it. And through this process, we found a distribution with 5 atoms that achieves a probability of 0.4.
Wow. So you actually found a distribution that works.
We did. But it wasn't just random guessing. It involved a lot of systematic testing and adjustments.
I can imagine.
But the interesting thing is that even though this process was numerical, it still gave us some insights into how this problem behaves.
So numerical experimentation can actually be a valuable tool for mathematical discovery.
Absolutely. It's not just about brute force calculation, it's about using computation to help us understand the underlying patterns.
Right. So finding a good lower bound is great, but we also want to know how much room for improvement there might be.
Exactly. And that's where lemma 2.3 comes back into play.
That lemma that puts an upper limit on the probability.
Right. And the key to using this lemma effectively is understanding how it depends on this parameter.
Okay.
Yeah.
So the bigger the m, the tighter the bound we get.
Exactly. But of course, the calculations also get more complex.
Right. So it's a trade-off.
It is. And we started with a relatively small value of m equals 4.
Okay.
And we were able to calculate the upper bound by hand.
And what did you get?
For m equals 4, we got an upper bound of 916.
Okay.
But then we decided to try m equals 6 to see if we could get a tighter bound.
Were you able to do that one by hand as well?
We were,
Yeah.
and it turns out that for m equals 6, the maximum number of inequalities that can be satisfied simultaneously is 28,
Out of
a total of 60.
okay.
So that gives us an upper bound of 2860, which is about 0.467.
So we did get a better bound.
We did, but as you can imagine, the calculations got significantly more complicated.
Right? So what about even larger values of m?
Well, that's where things start to become too complex to handle manually.
Because the number of combinations just explodes.
Exactly.
Yeah.
So to tackle this problem for larger values of we had to bring in some heavier computational tools.
Like what?
We used something called mixed integer linear programming, or MILP for short.
MILP. Okay, I'm not familiar with that. Can you explain what it is?
Yeah, so MILP is a way to solve optimization problems where some of the variables are restricted to be integers.
Integers meaning whole numbers.
Right. And in our case, we used MILP to find the largest possible set of inequalities that we could satisfy at the same time for a given value of milk.
So you essentially taught MILP how to understand our problem.
Exactly. We had to translate our mathematical problem into a format that MILP could work with.
Okay. And what did MIL tell you?
Well, for m equals 15, the MILP solution found 200 and 304 inequalities that could be satisfied,
Out of first off.
out of a total of 5,460,
So that suggests an upper bound of.
about 0.422.
Wow. So that's a significant improvement from the 0.467 we had before.
It is. But there's a subtle point here.
What's that?
This MILP solution gives us a strong hint about the upper bound, but it doesn't actually prove it.
So we need to verify it rigorously.
Exactly. We need to go from its computational evidence to a solid mathematical proof.
And how do we do that?
We actually use MILP in a second way to help us with the proof.
Okay. So you used MILP to find the likely upper bound, and then you used it again to prove it.
Exactly. The first MILP helped us identify a candidate for the maximal set of inequalities that could be satisfied.
Okay.
But we needed to make sure that we couldn't add any more inequalities to that set without creating a contradiction.
Right. So the first MILP was like a scout finding a promising location.
Yeah, good analogy.
And then you need to bring in the engineers to make sure it's actually solid ground.
Right. So we designed a second MILP specifically to test whether a given set of inequalities was infeasible.
Infeasible meaning.
Meaning they couldn't all be true at the same time.
Okay.
And the way we did this was by dividing the set of inequalities into smaller subsets and then checking each subset separately.
So if you could show that all the subsets were infeasible,
Then we would know that the original set was indeed maximal.
like breaking a big problem into smaller pieces and proving that each piece is impossible.
Exactly. And our second MILP actually found 426 of these infeasible subsets,
Wow.
confirming that our initial set of 2,334 inequalities was indeed the biggest possible set.
So that gives us a rigorous proof for the upper bound of 0.422.
It does.
It's amazing how much computational power we had to use to solve a problem that started with a simple game of dice.
It's true. And even with all of this effort, there's still a gap between our lower and upper bounds.
Right, we still don't know the exact maximum probability for this inequality.
It's a mystery that remains to be solved.
It seems like every time we dig into these seemingly straightforward questions, we end up uncovering these incredibly complex mathematical landscapes.
That's the beauty of math. It's full of surprises, and there's always more to explore.
Welcome back to the final part of our deep dive into Beat the Average. We've been on quite a journey.
We have, from those non-standard dice
Yeah,
to these upper and lower bounds.
exactly. And we left off with that gap between those bounds for the probability of the inequality, x1 plus x2 plus x3 less than 2 times x4.
Right. We have that lower bound of 0.4
Uh-huh.
and the upper bound of 0.422.
But we still don't know the exact answer.
That's right. It's a reminder that even with powerful tools like MILP,
Right.
some problems just don't have easy answers.
Yeah, it makes you wonder if there's a more elegant solution out there.
Maybe something that doesn't require all that heavy computation.
Right. Some clever transformation or a different perspective that we haven't thought of yet.
It's definitely possible. That's what makes mathematical research so exciting.
Yeah. You never know when a breakthrough might happen.
Exactly.
So for our listeners who like a good mathematical puzzle,
Yeah.
we've got one for you. Could that lower bound of 0.4 actually be the true maximum probability?
Or is there some hidden distribution out there that gets us closer to 0.422?
Or maybe even beyond it?
That's the question. We leave it to you to explore.
Maybe a new tool or a fresh perspective is all it takes to crack this problem wide open.
It just goes to show that math is full of unsolved mysteries.
Absolutely.
Mm-hmm.
And even something as simple as a game of dice can lead to these deep mathematical questions.
That's the beauty of it. There's always more to discover.
So to all our listeners out there, keep those minds curious.
Keep exploring.
And who knows, maybe one of you will be the one to solve this puzzle.
That would be amazing.
It's been a fascinating deep dive.
It has.
And as always, thanks for joining us.
Thanks for having me.
We'll see you next time.